Hi everyone. Now we see about eigenvalues and eigenvectors. This is P. Nachammal, Assistant Professor, PG Department of Mathematics. Now we see one of the interesting topic in matrix theory, eigenvalues and eigenvectors. Now we already know about what is the matrix and the definition. Okay. Now we see the interesting and basic concepts of eigenvalues and eigenvectors. Recall our basic definitions in matrix theory. First of all, we know about matrix. Already we know what is the matrix. We arrange numbers in rows and columns in certain arrangement like row wise and column wise. Also, we know about order of a matrix, that is number of rows and columns are a order of a matrix. Similarly, we find determinant from the matrix, transpose of a matrix, identity of the matrix, and multiplication of two matrices, inverse of a matrix, symmetric and non-symmetric matrix, singular and non-singular matrix. Okay, these are the basic definitions. Already we know these definitions. Now we see only eigenvalues and eigenvectors. What is the eigenvalue? Now we initially see that the matrix definition: a system of mn numbers arranged in a rectangular arrangement along m rows and n columns and bounded by the brackets, that is like square bracket or parentheses, that is it can be written as A equal to, that is m by n matrix like can be written as A equal to A11, A12, etc. A1n, and the second row is A21, A22, etc. A2n, and finally the last row becomes AM1, AM2, etc. AMN. Now we write the characteristic polynomial. The characteristic polynomial can be written as determinant A minus lambda I. We will give a polynomial which we call as a characteristic polynomial of a given matrix A. Now we see the definition of eigenvalues. The given matrix A can be written as Aij, which is a square matrix. The characteristic equation of a matrix A is can be written as determinant A minus lambda I equal to 0. The roots of the characteristic equation are called the eigenvalues of A. The eigenvalues also called as latent value or latent root or characteristic value or characteristic roots of a matrix. Okay, now we see that the eigenvectors definition: A equal to Aij be a square matrix of order n. There exists a non-zero vector x which can be written as x1, x2, x3, etc. xn, such that Ax equal to lambda x. Then the vector x is called an eigenvector of A corresponding to the eigenvalue lambda. Now we find the method of finding characteristic equation of 3 by 3 matrix and 2 by 2 matrix. The characteristic equation of 3 by 3 matrix is written as lambda cube minus s1 into lambda square plus s2 into lambda minus s3 equal to 0. Here s1 is equal to sum of main diagonal elements, s2 equal to sum of minor and minor of main diagonal elements, s3 equal to determinant A. Similarly, we write the characteristic equation of 2 by 2 matrix is lambda square minus s1 lambda plus s2 equal to 0. Yes, here s1 equal to sum of the main diagonal elements, s2 equal to determinant of A. Okay, sum of the main diagonal elements is nothing but trace of the matrix. Okay, now we see some examples for finding the characteristic equation of the matrix. First problem, find the characteristic equation of the matrix 1, 2, 0, 2. Here we find the characteristic equation, use the form a lambda squared minus s1 lambda plus s2 equal to 0. S1 is nothing but sum of the main diagonal elements or trace of the matrix. Here we add the diagonal element 1 plus 2, we get 3. Similarly, if we find out the determinant of the given matrix, nothing but 2 minus 0 equal to 2. Now we get S1 and S2 and substitute S1 and S2 in the standard form, that is lambda square minus S1 is here 3, therefore 3 lambda plus S2 is here 2. So the equation becomes, that is the characteristic equation becomes lambda squared minus 3 lambda plus 2 equal to 0. Next we see the example, that is we find the characteristic equation for 3 by 3 matrix. Okay, 3 by 3 matrix. The matrix is 2 minus 3 1, 3 1 3, minus 5 2, minus 4. The general form of the characteristic equation for 3 by 3 square matrix is starting with lambda cube minus s1 lambda squared plus s2 lambda minus s3 equal to 0. Initially we know that s1 sum of the main diagonal elements, that is the trace of the matrix. Here matrix, the leading diagonal elements are 2, 1, minus 4. So we add these three elements. 2 plus 1 minus 4 equal to minus 1. So S1 equal to minus 1, and similarly S3 equal to determinant A. Nothing but we find out the determinant of the given matrix. We get the determinant value is 0 here. Now the additional one is S2. That is from the 2 by 2 matrix we find out S2 is different from 3 by 3 matrix. Okay, S2 equal to sum of minor of main diagonal elements. Here main diagonal elements are 2. So we excluding the corresponding rows and columns, we get 1, 3, 2, minus 4, and plus here the next diagonal element is 1. So we leave corresponding row and column, we get only 2, 1, minus 5, minus 4. Similarly the last diagonal element is minus 4. Corresponding rows and columns we leaving, we get only 2, minus 3, 3, 1. So we find the determinant value 1, 3, 2, minus 4 we get minus 10, and 2, 1, minus 5, minus 4 we get minus 3, and 2, minus 3, 3, 1 we get plus 11. Finally simplifying S2 we get minus 2. Okay, now we substitute S1 is minus 1 and S2 is minus 2, and finally S3 is equal to 0. Therefore the equation becomes lambda cube plus lambda squared minus 2 into lambda, and finally S3 value 0, which is equal to 0. So this is the characteristic equation of the given 3 by 3 matrix. 2, minus 3, 1, 3, 1, 3, minus 5, 2, minus 4. Now we find the eigenvalue of a given 3 by 3 matrix. So we find the eigenvalues. Initially we find out the characteristic equation. So the same process for applying the above example. Now we use the above concept for this example, that is lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. Similarly we find out S1 equal to, that is the trace of the given matrix, 1 plus 2 plus 1 we get 4, and S2 is equal to sum of the minor of main diagonal elements. Okay, here S2 equal to 3 and S3 equal to determinant of the given matrix, we get 0. So the characteristic equation is lambda cube minus 4 lambda square plus 3 lambda minus 0 equal to 0. So now we write the characteristic equation is lambda cube minus 4 lambda square plus 3 lambda equal to 0. Here we taking lambda outside, therefore the original characteristic equation becomes lambda into lambda square minus 4 lambda plus 3 equal to 0. So one eigenvalue is lambda equal to 0. We find out the remaining two eigenvalues, so we can factorize the equation lambda square minus 4 lambda plus 3. So we factorize this equation, we get lambda minus 1 into lambda minus 3. So initially we find out one eigenvalue, first eigenvalue lambda equal to 0. Now we find out the second and third eigenvalues becomes 1 and 3. Therefore the corresponding eigenvalues of a given 3 by 3 matrix are 1, 3 and 0. Now we see the properties of eigenvalues. The properties of eigenvalues are very important to know about eigenvalue concept. First one, the sum of the eigenvalues of a matrix is sum of the elements of the main diagonal. So we add the sum of the main diagonal elements as well as we add the sum of the eigenvalues. These are equal. Next we product the eigenvalues, we get the determinant of the given matrix. And suppose our matrix is a triangular matrix, maybe that matrix may be a upper triangular matrix or lower triangular matrix. The diagonal elements of your matrix is nothing but the eigenvalues of the given matrix. Okay, suppose if the matrix A have an eigenvalue lambda, means the matrix A have an eigenvalue lambda, the inverse of the matrix A inverse have the eigenvalue can be written as 1 divided by lambda. Here lambda definitely not equal to 0. Now we see the matrix A. The matrix have an eigenvalues lambda 1, lambda 2, lambda 3, etc. lambda n. Suppose A power m has an eigenvalues can be written as lambda 1 power m, lambda 2 power m, etc. lambda n power m. Now we see the sum of the eigenvalues and product of the eigenvalues of the given matrix. For example, the given matrix A equal to 2, 1, 2, 1, 3, 1, 2, 1, minus 6. Now we find out the sum of the eigenvalues and product of the eigenvalues. Okay, sum of the eigenvalues. Here we directly find out the eigenvalues of the given matrix because the given matrix is symmetric matrix. Okay, in symmetric matrix, the diagonal elements are the eigenvalues of the given matrix. So we easily find out the eigenvalues from the given matrix. Okay, so sum of the eigenvalues is nothing but sum of the diagonal elements. So 2 plus 3 minus 6 equal to minus 1. Similarly, we find out the product of the eigenvalue is nothing but determinant A. Here determinant value is equal to minus 40. Therefore, sum of the eigenvalue is equal to minus 1 and product of the eigenvalue is equal to minus 40. Okay, next problem based on the first problem. Here also given that the matrix is a symmetric matrix. Okay, previous sum we see the example that matrix is also a symmetric matrix. Here this matrix is also the symmetric matrix. Here they are given that the product of eigenvalues of a matrix A is equal to 16. Here we find out the third eigenvalue. We are given product of two eigenvalue is 16. That is lambda 1 into lambda 2 equal to 16. We know that the property of the eigenvalues, product of eigenvalue is nothing but the determinant of the matrix. So lambda 1 into lambda 2 into lambda 3 equal to determinant A. Already we know that lambda 1 lambda 2 is 16. Therefore 16 into lambda 3 equal to determinant of the given matrix. So 16 into lambda 3 equal to 32. Therefore lambda 3 equal to 32 divided by 16 equal to 2. Therefore the corresponding third eigenvalue is 2. Now we see the next example. Two eigenvalues of a matrix A equal to 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3 are 3 and 0. What is the third eigenvalue? Okay, here they are given also the symmetric matrix. Here also A is a symmetric matrix. Now we find out the third eigenvalue. We asking what is the product of eigenvalues of A. First we find out the third eigenvalue and then we finally find out the product of eigenvalues. We know that the property, that is the property of eigenvalue, sum of the eigenvalue is equal to sum of the main diagonals. Here they are given lambda 1 equal to 3, lambda 2 equal to 0, but we don't know lambda 3. So we add these eigenvalues lambda 1 plus lambda 2 plus lambda 3 equal to sum of the main diagonal elements is equal to 18. That is 3 plus 0 plus lambda 3 equal to 18. Lambda 3 equal to 15. So now we find out the third eigenvalue. Product of eigenvalue is nothing but the product lambda 1 into lambda 2 into lambda 3 equal to determinant A. Here 3 into 0 into 15 which is equal to determinant A. Therefore determinant A value is equal to 0. So finally, we conclude that the third eigenvalue is 15 and the product of eigenvalue of A is 0. Example, if 3 and 15 are two eigenvalues of the matrix 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3, then find the third eigenvalue, also find determinant A, and hence which is equal to determinant A, that is product of eigenvalue equal to determinant A. We prove that. Given matrix is also the symmetric matrix. Also given that lambda 1 equal to 3, lambda 2 equal to 15 and lambda 3 equal to, we also again apply the property of eigenvalues. Sum of the eigenvalues equal to sum of the main diagonals. Lambda 1 plus lambda 2 plus lambda 3 equal to 18. Now we find out lambda 3 equal to 0. So now the product of eigenvalue is nothing but lambda 1 into lambda 2 into lambda 3. Lambda 3 value 0. Hence we get determinant A equal to 0. So we prove that determinant A equal to 0. Therefore, here the third eigenvalue is 0 and the product of eigenvalue of A is 0. Now we some more examples, that is we deal with non-symmetric matrix with the eigenvalues are not repeated. Find the eigenvalues and eigenvectors of the matrix 1 minus 1 4 3 2 minus 1 2 1 minus 1. So as usual we initially write the characteristic equation of the given matrix, that is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. As usual process, s1 equal to nothing but sum of the main diagonal. Here s1 equal to 2 and S2 equal to sum of minor of main diagonal elements, we get S2 equal to minus 5, and S3 equal to determinant A, we get S3 equal to minus 6. Substituting these S1, S2, S3 in the characteristic equation, we get the characteristic equation is lambda cube minus 2 lambda squared minus 5 lambda plus 6 equal to 0. So here we get 3 eigenvalues. Initially, we solve the characteristic equation by using the synthetic division. So first we apply the synthetic division, we get one eigenvalue, that is lambda equal to 1, and the equation lambda cube minus 2 lambda squared minus 5 lambda plus 6 equal to 0 can be reduced into lambda minus 1 into lambda squared minus lambda minus 6 equal to 0. Here lambda equal to 1, and we factorize the equation lambda squared minus lambda minus 6 equal to 0, we get lambda plus 2 into lambda minus 3 equal to 0. Therefore, the corresponding eigenvalues are lambdas are 1, minus 2 and 3. Here the eigenvalues are distinct. We find out the corresponding eigenvectors for the corresponding eigenvalues. So for this we can apply the equation a minus lambda I into x equal to 0. So now we substitute A equal to the given matrix minus lambda into 3 by 3 identity matrix into x can be taken as the column vector x1, x2, x3 which is equal to 0. Now we rewrite the equation like that: 1 minus lambda minus 1 4, 3 2 minus 1 minus 1, 2 minus lambda minus 1, 2 1 minus 1 minus lambda into x1 x2 x3 equal to 0. So we write the equation from the above matrix equation. We get 1 minus lambda minus x2 plus 4x3 equal to 0, 3x1 plus 2 minus lambda into x2 minus x3 equal to 0, 2x1 plus x2 plus minus 1 minus lambda into x3 equal to 0. So now we substitute the corresponding eigenvalues starting with lambda equal to 1. So lambda equal to 1, the above system of equations can be reduced into 0x1 minus x2 plus 4x3 equal to 0, 3x1 plus x2 minus x3 equal to 0, 2x1 plus x2 minus 2x3 equal to 0. Now we solving these equations by cross multiplication rule. So we write like that: x1, x2, x3, minus 1, 4, 0, minus 1, 1 minus 1 3 1. So x1 by, so as usual cross multiplication, so x1 divided by 1 minus 4 equal to x2 divided by 12 minus 0 equal to x3 divided by 0 plus 3. So we get x1 divided by minus 3, x2 divided by 12 which is equal to x3 divided by 3. Now we divide all the parts with 3, we get x1 divided by minus 1, x2 divided by 4 and x3 divided by 1. So therefore the corresponding eigenvectors for lambda equal to 1 is x1 equal to minus 1 4 1, and the second now we substitute lambda equal to minus 2 in the above system of equations. Therefore the system of equations becomes 3x1 minus x2 plus 4x3 equal to 0, 3x1 plus 4x2 minus x3 equal to 0, 2x1 plus x2 plus x3 equal to 0. Again we applying the cross multiplication rule, we solve the above system of equations like that: x1, x2, x3, as well as we find out x1 divided by minus 15, x2 divided by 15 equal to x3 divided by 15. Overall we divide 15, so we get x1 equal to minus 1, x2 equal to 1, x3 equal to 1. Therefore the corresponding eigenvectors for the eigenvalue lambda equal to minus 2 is x2 equal to minus 1 1 1. Similarly, we again substitute lambda equal to 3 in the corresponding system of equation. Again we frame the system of equation and then we solve the above equations by cross multiplication rule, and finally we get a eigenvector for the corresponding eigenvalue 3. Therefore the result becomes the eigenvalues of 1 minus 2 3 and the corresponding eigenvectors of 1 is minus 1 4 1, minus 2 is minus 1 1 1 and 3 is 1 2 1. Okay, next we see that the example for non-symmetric matrix with eigenvalues repeated or repeated eigenvalues. Here also we write the characteristic equation and find s1 s2 s3 and substitute the same process in the above example. So here the given example, the characteristic equation becomes lambda cube plus lambda square minus 21 lambda minus 45 equal to 0. As it is, we use the synthetic division to find the first eigenvalue. The first eigenvalue is minus 3. Okay, after that the equation reduced into lambda square minus 2 lambda minus 15 equal to 0. Again we get the eigenvalues becomes one is 5, another one is minus 3. Okay, here the two eigenvalues are repeated like that, minus 3 minus 3. So here also we find out the eigenvectors for the given matrix, as well as we apply the equation a minus lambda into x equal to 0. We frame the system of equation minus 2 minus lambda into x1 plus 2x2 minus 3x3 equal to 0. 2x1 plus 1 minus lambda into x2 minus 6x3 equal to 0. Minus x1 minus 2x2 minus lambda into x3 equal to 0. First we substitute in the case 1 lambda equal to 5. So the above system of equation reduced into minus 7x1 plus 2x2 minus 3x3 equal to 0. 2x1 minus 4x2 minus 6x3 equal to 0. Minus x1 minus 2x2 minus 5x3 equal to 0. So solving the above equations by using the cross multiplication rule, we get x1, x2, x3 is 1, 2, minus 1. Therefore the first eigenvector is 1, 2, minus 1 for the corresponding eigenvalue lambda equal to 5. Now we see the second case, lambda equal to minus 3. The above system of equation, that is equation number 1, becomes x1 plus 2x2 minus 3x3 equal to 0, 2x1 plus 4x2 minus 6x3 equal to 0, x1 plus 2x2 minus 3x3 equal to 0. Here number 5, 6, 7, the equations are all same. So we consider only one equation. In that equation we put x1 equal to 0. So x1 equal to 0, therefore the equation becomes 2x2 minus 3x3 equal to 0, which implies 2x2 equal to 3x3. 2x2 divided by 3 equal to x3 divided by 2. Therefore the eigenvector becomes x2 equal to x1, x2, x3. x1 is here 0, x2 is 3 and x3 equal to 2. Therefore the corresponding eigenvector for the eigenvalue lambda equal to minus 3 is 0, 3, 2. Next we put x2 equal to 0. Therefore the equation becomes x1 minus 3x3 equal to 0, x1 equal to 3x3. From that x1 divided by 3 equal to x3 divided by 1. Therefore the corresponding eigenvector for lambda equal to minus 3, which becomes 3, 0, 1. Therefore the eigenvectors are minus 1, minus 2, 1, 0, 3, 2, 3, 0, 1 for the corresponding eigenvalues. Next we see that symmetric matrix with non-repeated eigenvalues. Here the example becomes 1, 1, 3, 1, 5, 1, 3, 1, 1. The given symmetric matrix, we write the characteristic equation of the given symmetric matrix, which becomes lambda cube minus 7 lambda squared plus 0 lambda minus 36 equal to 0, as well as we find out the eigenvalues of the given characteristic equation. For that we apply the synthetic division. We find out the one eigenvalue is minus 2 and the remaining equation becomes lambda square minus 9 lambda plus 18 equal to 0. We get the eigenvalues lambda is equal to 3, 6. Here find out the eigenvalues. These eigenvalues are all distinct. Okay, now we find out the eigenvectors. So as well as we form the system of equations from the original equation a minus lambda into x equal to 0. So we substitute the first eigenvalue lambda equal to minus 2. We form a system of equation and then solve the equation by using cross multiplication rule. We get x1 is equal to minus 1, 0, 1, and in the second case we apply the second eigenvalue lambda equal to 3 in the above system of equation 1. We get the system of equation. Again we apply the cross multiplication rule. We get x1, x2, x3. We minus 1, 1, minus 1. Therefore x2 equal to minus 1 for the eigenvalue lambda equal to 3. Now finally we substitute lambda equal to 6 in the above system of equation. That is the equation number 1. We get the equation like that, minus 5x1 plus x2 plus 3x3 equal to 0, x1 minus x2 plus x3 equal to 0, 3x1 plus x2 minus 5x3 equal to 0. Again we apply in the cross multiplication rule. We get x1, x2, x3 equal to 1, 2, 1. Therefore the eigenvalues are 6, minus 2, 3. We get the corresponding eigenvectors of the eigenvalues are minus 1, 0, 1, minus 1, 1, minus 1, 1, 2, 1. Okay, next we see the example for symmetric matrix with repeated eigenvalues. We already know that from the previous examples how to form the characteristic equation in the above or previous examples. Okay, now we directly move on to the characteristic equation of the given matrix. Lambda cube minus 12 lambda square plus 36 lambda minus 32 equal to 0. Now we apply the synthetic division. We get lambda equal to 2 is a one eigenvalue, and we find out the remaining eigenvalues from the equation lambda square minus 10 lambda plus 16 equal to 0. We get lambda equal to 8 and 2. Therefore the eigenvalues becomes 8, 2, 2. So here 2 is the repeated eigenvalue. Now we find the eigenvectors for the corresponding eigenvalues. For that we substitute lambda equal to 8 in the above equation, a minus lambda I into x equal to 0. So we get the system of equation like that: minus 2x1 minus 2x2 plus 2x3 equal to 0, minus 2x1 minus 5x2 minus x3 equal to 0, 2x1 minus x2 minus 5x3 equal to 0. Again we apply the cross multiplication rule. We get x1, x2, x3 is equal to 2 minus 1, 1. Therefore the corresponding eigenvector x1 is equal to 2 minus 1, 1. Next we substitute lambda equal to 2 in the second case. For that we get a system of equation: 4x1 minus 2x2 plus 2x3 equal to 0, 2x1 plus x2 minus x3 equal to 0, 2x1 minus x2 plus x3 equal to 0. So the equation 4, 5 and 6 are the same equations. So we take one equation: 2x1 minus x2 plus x3 equal to 0. Here we put x1 equal to 0. We get x2 equal to x3. Therefore the corresponding eigenvector x2 becomes 0, 1, 1. And then next we take the last eigenvector x3 equal to LMN, which is orthogonal to the previous vectors x1 and x2, because the given matrix is symmetric. Therefore we already find x1 nothing but 2 minus 1, 1 into LMN, which is equal to 0. So after the matrix multiplication we get 2L minus M plus N equal to 0. Similarly, we multiplying L, M, N with the second eigenvector x2, we get 0L plus M plus N equal to 0. Now we solve the equation 7 and 8 with cross multiplication rule. We get L equal to minus 2, M equal to minus 2 and N equal to 2. Therefore, the corresponding eigenvector x3 equal to 1, 1, minus 1. We know that already the eigenvalues of the given matrix is 8, 2, 2, and the corresponding eigenvectors are 2, minus 1, 1, 0, 1, 1, 1, 1, minus 1. So for my references, eigenvalues and eigenvectors, I also include this video link and my reference book. Thank you all.